So this is a weird week because it's not really focused on coding at all. It's more stepping back to understand when we use statistics to understand the world, what do we actually mean by that? And it's not entirely necessary to understand what I'll talk about today, because if you can understand the steps we'll do later, that's all you have to understand. But for some people, understanding sort of the machinery behind um, what we're doing can be useful. So I don't know. I'm going to I'm going to apologize. I'm kind of zonked before we even start this. So today I got out the second of two papers I've written on coronavirus, because I don't know how to react to coronavirus other than to research it. But trying to complete two new projects while on quarantine has not been easy. And so I feel incredibly unprepared for this and just exhausted. And this is a really esoteric concept to go over. So we'll see how it goes. So please slow me down at any point and ask questions, and we can get through this together. A lot of this is going to go over what is in the textbook, but I didn't actually reread the textbook for it. So it's kind of like reading it from somebody else. And so I think it'll go along well with what I wrote there. And so that's another chance for you to get a handle on what I'm talking about. So I don't know. I mean, I don't need to keep yammering on about what we're going to do. We might as well just do it. We'll start by going over the last week's lab. I guess before we start, does anyone have any questions about either the final or anything else?
So last week's lab was the charts.
Yeah.
That was new.
Yep.
I think just initially gazing at it, it was real intimidating. But once we got into like actually physically doing it, the instructions were there in the book, so it was more intimidating on the front side than once you actually got in. It was time consuming, but it was workable.
I'm glad. So, I mean, that's good to hear. I mean, it's one of those things where if you start from trying to get all 8 pieces of the code in the first go, that's a lot harder. Sort of the idea of the basic plot and the more advanced plot was to see how you can build it iteratively and getting sort of the first part down and then seeing what you can add to build it out. But yeah, I was really impressed by everything that I saw from everyone. Everyone seemed to get a handle on it. And it's just a thing that takes practice. It's, just takes some time to get comfortable with. And then once you sort of get a handle on the commands, outputting really good looking graphs and figures becomes almost automatic.
And we do have the option, if I read your email correct, we do have the option to either do our final project
Mm-hmm.
in either R or on an Excel spreadsheet.
Yeah, or whatever you would like to do.
But there won't be any points taken off if we don't do it in R?
No.
Cool.
So if you already have sort of some skills in Excel, that might be a better option for people. I taught this class for undergrads years ago in Excel because I thought it would be more understandable and digestible. You have all the data sitting in front of you to work with. But it actually is really complicated to do much in Excel because I spent so much time going over select this cell and enter the dollar sign so you're keep in it. But it's also so limiting because there's not so much that you can actually do in Excel. So you can, get through the assignment is sort of the goal. If you can do it easier in Excel, do that. If you want to follow along what we're doing in R, you can do that. Your decision, it's up to you. It's up to each student. I've had people say that they're going to take that route. Others want to stick with it. So, it's up to you, as they say. Any other questions before we go to something else? Or before we begin reviewing the lab? All right, let's jump in. So I'm going to share my screen, and then we'll go from there. Okay, I have the chat up. So you can either put a question in the chat or just whatever it is you need to do to signal that you would like to ask something. So starting by reading in the data so that I can work with it. I've got this data on California schools now. Did I already fill these in? I guess I did. Yes. So I can't even remember what I did this morning. So this is the basic graph of a bar plot of the grades at California schools. I apologize if I was unclear about what variable I wanted you to use here. The grades variable shows the grades at each school. And if we put that inside of a table so that it counts how many of each grades observation there is and put it with bar plot, it'll give us a pretty basic bar chart that shows how many K through 6 schools there were and how many K through 8 schools there were in the data. That's the basic plot of this. And then for further practice, I said you could change the color, change the length of the y-axis so that it goes up to 500 and give it an appropriate title. And so I add call equals steel blue, ylim equals C0 500, and main equals type of school. And this is what that looks like. Any questions on the bar plot?
I have a question.
Yes.
So you need to, it looks like insert a table or something. Or
Yeah.
I was looking at, there must have been some other help online that did it as like counts or something before a bar plot every time. Even after you're reading the data, you need to do something else in order for it to create a bar plot. But with plot, you don't need another table or counts or things like that. Is that right?
Yeah, so if your data came in sort of originally as, no, I don't want to do this on the fly, it's gonna go bad. So if your data came as the table already, if this is what your data came in as originally, if you had it as counts of different things, you wouldn't have to create the table. But the reason we have to do the table is to get this information. And so if you started with these two variables, K6 and K8, and 61 and 359, you could graph that in a bar plot automatically. But because most data isn't itself a count, you want to use the table in order to create that. You could also, so if I save this grades table, I could save this as its own object. And then instead of putting that here, I could do this. And I think I do this in the book once because I didn't actually, because I was getting myself comfortable using creating a bar plot. So this is another way to do it if that's easier for anyone, or to make it sort of more iterative. But what a bar plot wants is a list of the things a list of the categories, K6, K8, eye colors, and the number of observations, the count of each of those things.
Okay, cool, thanks.
Any other questions about bar charts? Okay, scatter plot. So like Liz was saying, with a scatter plot or most other plots, we can just put in the names of the data directly. We don't have to create a table. So this is asking you to put expenditure on the x-axis, read on the y-axis, and this would be our basic scatter plot for those. And for the further practice, I asked you to label the two axes, make the box into an L shape, change the color, and change the shape of the points. I rarely do anything other than PCH equals 16. So I enjoyed seeing everyone's different shape of the plots. But so X lab equals school spending, Y lab equals reading test scores, B2Y changes the box shape, box type is what that's short for. Call equals tomato 4 I chose, and PCH equals 4, which is these nice little crosses. Any questions about scatter plots? All right. Histograms, which we'll see a lot of tonight. So the basic command for a histogram is hist, and then you give it one column of data. So here we're doing with California with schools, or with California school students. So what the histogram shows you is that a few schools have a lot of students out here, but most of these schools have fewer students than the sort of large extreme at the right end. Most schools have less than 5,000 students, which isn't too surprising. For further practice, I said to label the x-axis and change the color. And so with a histogram, and I may not have mentioned this before, there's two things you can change the color on, and this is true for a bar chart too. You can change the fill color of the bars. You can change the border with border equals. And so you can see that here, that there's two colors. And I changed the x-axis with xlab again. And I misspelled students. Any questions on histograms? And these lecture notes are already posted. If anybody wants to look at them later. And then so for the line graph, I gave you this data. So each time you generate this data, you will get different data because this random norm, our norm, is giving you a random list of 28 numbers, and it will give you a different list of 28 numbers every time you run it. So no two graphs will look the same. It will keep changing. That's great to generate random data, that can also make it difficult because then it keeps changing. So this would be the basic line graph with those two and this random run of the data. I asked you to do a few things here because this is probably going to be the graph you'll use in your final project. So some of this was getting you sort of used to it. I told you to label the y-axis as days, which doesn't make sense because that should go on the x-axis. Most of you figure that out. You should label the x-axis as whatever your experiment involves. I said to draw a line where your experiment occurs, change the color of the line, and write words on the graph. And so this is one example of how you can do that. So most of this we've seen before. The color, I changed the thickness of the line with LWD, line width. But then I add this AB line, which is a vertical line here at the 14th point. And then for text, my data randomly generated that away. These are the problems with randomly generating data. That is way too high. I will lower this. So you're telling it where on the graph specifically. Where to graph it. So this is 0.8 between 5 and 10, 8 and 105 on the 105. And so you can see that if I wanted to move it to 5, 110, I could do that. You could see, you can imagine sort of a grid here if you wanted to build it out. You could think about where to put it. Because this data keeps moving, if I tried to sort of move this off of the line would then move, and so it wouldn't really make a difference. But this is sort of the idea of how to label things on your data. for your final project, right, you might want to label whatever happened on this day, right? You might want to label sort of the low point, the different things that are going on to curate the graph. But that's something we'll keep working on as we go.
Real quick.
Yes.
So that's where things got a little tricky, moving that line. Like that's like we just couldn't get it to move. Like,
What do you mean by moving the line?
The dotted line?
Okay.
That one.
Yeah. So that's in this command, AB line. So V equals 14. So it's a vertical line at 14. If I moved it to 20, right? So whatever I make V equal, it'll draw a line at that point. And if I wanted it to be horizontal, I could do H equals 100. And now I have a horizontal line there. Does that make sense? Yeah, I mean, I don't know why that's AB line. It's just something you either use enough to memorize or you look up each time. All right, so that was the last question of the lab. Any questions on the lab or anything we've done before to this point? Okay, like I said, the labs looked really good last week. I was really pleased with what everybody showed, and so great progress. Awesome work. Okay, so this week we're gonna do a really brief recap of probability. We could do an entire week on probability because probability is interesting and useful and exists in your life whether you use statistics a lot or not. But there's a couple of, but we're going to skip a lot of that and these questions about whether you should buy the insurance plan on your cell phone or not, and try to extract the points about probability that we need for future weeks in understanding statistical analysis. And so we're going to do a really brief recap really on just the vocab we need from probability and how probability is used. And then we're going to talk about this idea of the central limit theorem. Has anyone heard of the central limit theorem before? And as I ask that, I don't really know how I would expect you to signal.
No.
Okay, cool. That's awesome. Because the central limit theorem is the coolest thing ever. So I'm excited to be the one that gets to introduce you, everyone. Okay. So I'm not just going to read these lecture notes. These are the sort of curated for people that aren't able to come to class. But probability, in my sort of simpleton understanding of it, is just referring to the measurement of chance. And there's two ways that we can express probabilities, which you've probably heard of. Odds, which are fractions, a 1 in 4 chance, a 1 in 5 chance, 3 to 1 odds if you're a gambler, or as probabilities, which are just those fractions divided. So a 1 in 4, if the odds are 1 in 4, it means that the probability is 0.25. Probability goes from 0 to 1. And a lot of statistics is going to use probabilities. We're going to keep seeing this term of a p-value. And just a p-value means the probability, which goes from 0 to 1. And p-values are going to become really important in sort of the last weeks of where we're going. But so probability, odds, chance is all just expressing the odds of things happening. And what it's expressing is how likely is something to occur. We can't prove that odds are wrong on just one instance. Even if something unlikely occurs, it doesn't mean that the odds were set too high. We can only know if the odds were set too high with repeated observations. So even if the weatherman says that there's only a 10% chance of rain and it rains all day, that doesn't mean that they were wrong. It just means that that was the 1 in 10 chance actually occurring. And weather is one place where we see this a lot because the chances of rain are always expressed as probabilities. And uniquely, weather people are actually pretty good. So this is coming from, this graph is from Nate Silver's The Signal and the Noise. And they tracked weather forecasts for a long time to see how accurate they were. And so what you would expect, or what your sort of baseline is, that if the weather person says that there's a 10% chance of rain, on 10% of those days, there should be rain. There's only a 10% chance of rain, 10% of days with that prediction, there should be rain. And if there's a 50% chance of rain, half of days with that sort of prediction, there should be rain. And so this middle, this black line is sort of the perfect prediction. And there's 3 colored lines on this for the National Weather Service, the Weather Channel, and your local TV meteorologist. And what you can see is that this blue line, which is for the National Weather Service, is actually pretty close to perfectly accurate. If they say that there is a, what's this here, 30% chance of rain, 30% of the time it does rain. Over sort of 1,000 observations, they are very close to perfectly accurate in the odds of it raining that day. The Weather Channel is actually pretty good as well. Just right, they're almost spot on at 90, 80, 70. Most of these, they're very close. If they say that there's a 50% chance of rain, half of the time it will rain on those days. The one that's a little further off is your local TV meteorologist. So if the line is on this side, this is their predicted probability of rain. And this is the observed frequency on the X. And so if the TV weatherman says that there is a 50% chance of rain, this point here, it only rains about 30% of the time. The local TV meteorologist sort of systematically over predicts the chances of rain. This is where in class I would pause and ask if anyone has a guess why that is. But I'll just sort of jump to the cut because Zoom is really awkward. The reason that local meteorologists do that is because they're afraid of people going to work without an umbrella. And so they always tell you it's going to rain more than it will, just so that you're safe and so that they don't get blamed, even if it's just sort of the odds. Because they could pull the weather forecast from the National Weather Service. Those are freely available to them. But they still overpredict rain just to cover their own bases, is the kind of way to say that. So anyways, so we can evaluate how well weather people do by looking at sort of the long run observation of whether their predictions are correct. And this came up a lot as sort of a big contentious point after the 2016 election, when Nate Silver and other statistical prognosticators gave Hillary this really high probability of victory. Based on everything that they were seeing, they said that there's a 70% chance that Hillary will win. And obviously Hillary did not win. And so there was this discussion about whether those odds were given too high, whether they weren't taking everything into sort of consideration. And there's also a recent paper that showed people that looked at that analysis were less likely to vote, because when they saw this sort of high probability of Hillary winning, they decided that she had already won. And so they didn't go and win. And so there's actually a theory that statistical prediction caused Hillary to lose. But that was sort of a one-off occurrence, right? We don't know whether the odds or probability were correct in that instance without looking at sort of the long-term sort of repeated predictability. But what probability and odds give us is this idea of how likely something is to sort of occur. And when we do know how often something should occur, probability gives us this opportunity to think about whether something improbable is going on. And so a lot of this goes back to just sort of to simple concepts of gambling, like flipping a coin. And you know that flipping a fair coin should give you 50% heads. 50% of the time that you flip a coin, you should get heads. 50% of the time you flip a coin, you should get tails. But we also know that flipping a coin twice won't guarantee one heads and one tail. That will even out over the long run, but you can get 2 heads in a row and 2 tails. You can get many heads and many tails in a row. But over time, it should lean towards closer and closer to 50% heads and 50% tails. But so we can look at some of this in sort of a long range view. And you don't need to worry about what all of this is. This is just a coin flipper, which I found online. And what this is going to do for us is it's going to flip a coin 100 times, and it's going to do that 30,000 times. And so flipping a coin 100 times gives us this sort of sample that should converge towards 50 heads and 50 tails, but not exactly. And doing it 30,000 times will sort of give us multiple samples from this fair coin. And so you can see that this is a fair coin, whether you care or not, because this is set to 0.5. And so when I run this, it gives us this histogram of all of the coin flips. So we flipped a coin again 100 times, and we did that 30,000 times. And this histogram gives us a picture of the distribution of those, and that most of the coin flips ended up close to 50. So this is the count of heads. So up here, 60 would be 60 heads, 40 would be 40 heads. This is the count of heads from the coin. And so you can see that most of the coin flips end up around 50, but not exactly. They pewter out on both sides. And so even though we know how many heads we should get, we don't get exactly that many heads every single time. But because we do know what we should get, we can detect if anything is, if there's a deviation over time. And that's how we would figure out if somebody had an unfair coin that they're flipping. So here we flip both a fair coin and an unfair coin. So this one gives heads a probability of 0.52. And so you can see that the fair coin has this distribution based around 50, and this unfair coin is slightly off. They're both really similar, but you can detect this slight deviation with this coin that is different. It would take a lot of flips, a lot of rounds to actually realize that the two coins were different. But given enough iterations, you could figure out that the second coin is cheating. All right, have I lost anyone?
A little bit, but what is the frequency referred to? If there were 30,000 flips, how come the y-axis only goes up to like 3,000 on the 2,000 on the first one and 1,500 on the second one?
Right, so the frequency is the count. And so
Count of
the count, then, so what this is reporting, so this is counting the number of heads. And so there were about 2,500 flips with 50 coin, or with 50 heads.
I thought it was 30,000.
So there's 30,000 total flips, but that's spread across all of these.
Okay.
So there were 2,500 for 50 and 2,400 for 52 and 2,200 for 54. And so you add all of these up,
Okay.
and it would become 30,000. But the sort of the most common was 2,500. Let me see. So that's a good question. So these are all of the individual counts of heads. So the first time we ran it, out of the 100, we got 42 heads, then 59, then 47, then 55. And so this list goes on for, so you see 1,000, there's 2,900, 29,000 hidden. And so you take all of these, you break them into sort of intervals, I think of 1 here, and you count up how many there were. So 24 and 11 for 49, 2404 for 50. So the data might be even more spread out than you would sort of expect, right? But all of that adds up to 30,000. And then it sort of gets scrunched here. This is 2,500 here too. But the y-axis is a little more squished. All right, so that's a really brief introduction to probability. How would I quickly summarize that? Probability is just telling us the chances of things, but each iteration we don't really know how to evaluate the odds. But stats gives us tools to do that. I don't know. I said that this was going to get a little esoteric. Stick with me. We're going to get to some really exciting stuff. And we'll loop back to coins at the end, I think. So that's probability. So let's dive into the central limit theorem, which is the powerhouse of sort of inferential statistics. And what we want to do in inferential statistics is be able to say something about data we don't have. Because the data we have is limited, and we want to be able to say things beyond that. And so the tools of inferential statistics allow us to do that. But first, just some vocabulary to make sure that we're on the same page. And this is all a review to some degree. So a population is everyone within a study, all students, all voters, all people, all coins. In this sort of example, the population would be 30,000 sets of 100 coin flips, right? It's the total unit of everything that we could be studying. And a sample is just a subset of those. So each time that we flip the coin 100 times, that's taking a sample of the coin. And the population of those is the 30,000 sets of those. And so it's similar to if there was a town of 30,000 and we take a sample of 1, you can think about sort of those units together. And the distribution is just all of the values in our data and the shape of those values. And so you can think about the incomes of everyone in the United States. All of the incomes of people have a certain distribution, a certain shape to them. And if we sort of collected data on the incomes of the population of the United States, we would be able to see the distribution of all of those incomes. And distributions come in a lot of different shapes. So one that we're going to talk about a lot is sort of a normal distribution. But They come in really weird collections with JAGs. They come in what's called a left skew or a right skew. When you take sort of all of the data of any sort of group, there's no single form that that data should take. The data just is whatever it is. It can have different spreads. It can have different sort of highs and lows. The data is what it sort of is. Are there any questions on that? What I mean by distribution? Okay, so one really important distribution of data is a normal distribution, which we're going to end up using a lot. And so a normal distribution is important because it has a really specific shape. And what a normal distribution is, it's all, you can think of it as a bell curve. That's another name for it. But the data is evenly distributed above and below the mean. And what that means is we know where data should fall relative to the mean in a normal distribution at all times. So here I've created a normal distribution with a mean of 100. And the great thing about a normal distribution is that within one standard deviation of the mean, 34.1% of the data will fall. When we talked about standard deviations before, I sort of talked about that most of the data will fall within one standard deviation. A lot of the data will be within two. You know, outside of that is sort of that anything sort of above 2 standard deviations is generally really good. But with a normal distribution, we know exactly how much of the data falls within 1 and 2 standard deviations, or any number of deviations. We know exactly how much data. So within 1 standard deviation, plus or minus of the mean, 68% of the data will fall. Within 2, roughly 95% will fall. Within 3 standard deviations, 99% of the data will fall within 99% of the data will fall within 3 standard deviations of the mean, plus or minus. And this is true for a normal curve just has a set shape. It's just a single shape of data. And they rarely occur in sort of nature. Some things are set up to take a normal curve. So IQ tests are written in such a way so that their takers will have a normal deviation. And so the average IQ will fall at 100 in sort of all times. And so that gives you sort of a comparison to look, and if you're 2 standard deviations above the mean on that, that's sort of where we know that you're more intelligent than most people, or specifically more intelligent than 95% of people. And so the normal curve is really important because we know where data falls. And that's important because if we take samples from a population, they will always form a normal curve. If we take repeated samples from any population and measure the mean, they will always form a normal curve. So here what I'm going to do is I'm going to create 3 distributions of data, some messy data, a left skew and a right skew. And I'm going to take samples out of those data, out of those distributions. And I did this in the fall. I did it over 3 days, and it was easier to break it up. It's a lot to do, and this is going to be a lot to do in one night, I'll tell you now. But we push on. But so what I'm doing here is I'm taking samples. So I'm taking samples from these data sets, from this graph, from this graph, and from this graph, from this distribution. And I'm taking groups of 60. Each of these distributions, each of the populations on these graphs is 100,000. So you can think of it as 100,000 people that live in messy distribution land and left skewed distribution land and right skewed distribution land. And I'm taking repeated samples of 60 of those, only 60 people out of the 100,000. And I'm calculating the mean on whatever I'm interested in. And I'm taking 5,000 samples. And as I take those samples, some of the means will be above the population mean, some will be below the population mean, just like when I was flipping the coin. But over time, the means from those samples will always form a normal distribution, no matter what the underlying distribution in the population is. Anyone have any questions at this point? Or are you all so flummoxed that you don't even know where to start?
Can you just like repeat what you said?
Absolutely.
Okay.
That's the easiest thing for me to do. No matter what the distribution in our population is, if we take repeated samples of it, the means of those samples will form a normal distribution. So the difficult thing is that I haven't gotten to like the cool part yet.
I have a question.
Yeah.
Are we, I mean, I'm trying to understand what we're trying to learn here. Is it just to make these fancy graphs in R so that we can use our own data? Or, I mean, we're like really trying to learn the statistics, because like, I don't know statistics clearly, but I mean, is this just a function of trying to learn how to apply R Markdown, you know, to whatever data set we come up with at our report? Or is this just more general esoteric for our knowledge and we won't really have to get this much into the weeds? At least
So
for this class.
yeah. So so the goal here, so next week, what we're going to try and do is be able to test whether something makes a difference. And the way we can do that in statistics is based on the central limit theorem. So let me sort of jump ahead, I guess, actually. I'm going to jump to sort of the end to answer that question of like, so I'm going to start with why do we care? And then I'll go back to how we can figure out whether we care. So let's say that next semester I have 2 classes. I'm teaching the same class twice. I have 2 sections. And I decide that with one of my sections, and I've taught this class for many years. This is sort of the distribution of sort of the class's average on my final test. The average for the class is around a 75. Some of my classes do much better. Some of my classes do much worse. The data sort of spreads out around the 75. In the same way as when we flip a coin, some of the iterations of flipping the coin are above 50, some of them are below 50, but they cluster around sort of the middle. And with my 2 sections next semester, what I'm going to do, what I want to see is whether singing my lecture improves my students' performance. I have this idea that singing my lecture will make them learn better. And so I want to test whether that happens. And so I'm going to have the students take these final tests in both class. And so in my class that I sang to, the final grade is a 79.3. The average for my students is a 79.3. And in the class that I didn't sing to, they got a 73.8. And the question is, though, is that a larger difference than I would expect by chance? Because if we go back to the coin flipping example, all right, if we go back to the coin flipping example, this is a perfectly fair coin that we flipped 30,000 times. And I could get a result as large as 60 here, which is a lot of heads, but that was done with a fair coin. There is no difference between the coin that I got 60 heads with or the coin that I got 50 heads with or that I got 40 heads with. This is all just generated by random chance. And so with my 2 classes next semester, what I ended up with is a 79 and roughly a 74. And so can I conclude that singing actually improved my students' scores? And how can I actually make that conclusion is sort of the big question. And what that goes back to is how we're using and what the central limit theorem provides us. Because that same question of does my singing improve my students' scores is the same question of how would we know if giving out free lunches at school improves students' retention? Or does giving loans to small businesses help them grow? Or does any number of sort of different policies or programs actually make a difference? It's the same question underlying your experiments. Does waking up earlier in the morning help you lose weight? And thinking about how would we actually know if that difference is larger? Because we know that sort of things are generated by chance. That taking repeated samples from any population will create these spreads of the data. Sometimes you flip the coin and you get 40. Sometimes you flip the coin and you get 50. Sometimes you flip it and you get 60. And so how do we actually know that something we did is just generated by random chance? And how do we know that it was generated by us actually doing something? And so the central limit theorem is the way that we can understand that. There's sort of math we can do the math we can do to understand that, and that scientists are using and that everybody is using to understand and answer those questions is based upon the central limit theorem, which is itself kind of esoteric and magical, but maybe is worth understanding. I'll be honest, nobody really told me about the central limit theorem until I don't remember anyone telling me about the central limit theorem while I was in school. But when I read about it in the best stats book I've ever come across, and I would recommend this to anybody, it's called Naked Statistics. And what it is, it's statistics written for common people. Understanding the central limit theorem makes everything that I was already doing a lot more clear. And so I don't know. If this doesn't help anyone, I can strike it from the record. But so that's the basic idea, right? How can I tell if these two numbers are different? And I can jump ahead. I think I've got it here, right? This is the mean for my score where I sang. This is the mean for my class where I didn't sing. How far apart do these two scores have to be for me to actually know that my singing made a difference? And so with that as sort of like a mean of preview of where we're going, I need to go back. So does anyone have any questions before I sort of try to go back to where I was, and more of the sort of esoteric buildup? Because I know you're on the edge of your seats to know whether my singing made a difference. Okay. I will take that as no. So when we take samples from any population and we calculate the means of those samples, they will form a normal distribution. And why that is important and good is because we know where data should fall in a normal distribution. We know that 68% of the data in a normal distribution will fall within 1 standard deviation of the mean, and that 95% of the data will fall within 2 standard deviations of the mean. And that's really, really useful. Yeah.
Question about this bell curve normal
Yeah.
distribution thing.
Mm-hmm.
It always falls that way because it's a way to organize your data into a bell curve, basically. I know that's like a weird way to say it, but I'm trying to get at like, right, it's always in equal relationship to the mean because the mean of any data is relative to the rest of it. And is that part of what you're sort of getting at, is like this is a step on the way to get to different answers that might vary and are useful in different ways, but this first step, like all sample data from a population will fall this way because that's what samples are.
To some degree, yeah. So it happens. So it happens naturally, but part of it is that we have to take a lot of samples to get a normal distribution. So this next set of charts is sort of changing the number of samples we take. So we're starting with this MEST data. Here we take 10 samples. This doesn't look like a normal distribution. 20 samples doesn't really look like a normal distribution. 50 samples, right? And we get up to 1,000 samples and we start to form a normal distribution. And so taking one sample can't give you a normal distribution. That one sample can fall anywhere within sort of the range of the data. It's only when we take a lot of samples that we're going to get a normal distribution. And then we know that 95% of those samples are going to fall within 2 standard deviations of the mean. And that's really important because we generally don't know the mean of our population. The reason that we know the reason that we can sort of say what the average income in the United States is because we take sort of a sample and figure out sort of the range around it, right? We generally don't start with knowledge about our population. That's what makes sort of the coin flip easy to understand, because we know that sort of the mean should be 50. But we generally don't know what the mean is. And so when we take the repeated samples, those together clustering in the middle show us what the actual middle is. It helps us to identify where that is on the graph. And so going back to the coin again, right, how do we know if a coin is fair? Right, and how would we know if a coin is fair just sort of in the wild? Because we know that the numbers we know that there's a wide spread in the distribution of heads with a fair coin. Right? We've already shown that. There were plenty as high as 60, there were plenty as low as 40. You can imagine that if you were sort of gambling on this and you were betting $1 for each head, against losing $1 for each tail. That if you played the game long enough, the two would even out and you wouldn't lose or gain any money flipping a coin. But within any sort of run of 10 flips, you could lose $8 or gain $5. And so we know with flipping a coin that most of the samples are going to cluster around 50. And 95% of them are going to fall within 2 standard deviations. So 95% of the samples were within 2 standard deviations of 50, which is 60 and 40. And so data can fall outside of that range, clearly. 5% of data is going to fall beyond 2 standard deviations of the coin. But what that begins to set up is not that something is impossible, but when it becomes improbable. And what the simpler explanation for something's behavior is. So if I flipped a coin, if we bet on flipping a coin and I got $1 for every heads and you got $1 for every tails, and I flipped my coin and I always got 70 heads, and so I made $20 a round, or I guess that would be $40 a round. That'd be $20 or $40. I made money each time we played. Right? Getting 70 heads is not impossible. Right? You can get 100 heads flipping a coin, but it is improbable. The odds of somebody flipping a coin and getting 70 heads are really, really low. The probability of that is less than 1 in 100,000. And if I did that twice playing with you, right, it isn't impossible, but it would be improbable. And the simpler explanation is that the mean for the coin I'm flipping is not 50 heads. It's something different than the population you would expect. And so the sort of important concept there is this idea of a true mean. We know that the true mean for a coin flip is 50. That the mean for the population of all coins flipped in all times is 50. And so because we know that true mean, we know that 95% of the samples will fall within 2 standard deviations. But where it becomes important then, because we're generally not flipping a coin, we're not getting 30,000 separate samples of the population to understand the country's income. We're only going to get 1 sample. But so the important thing is that the reverse is true for that sample as well. If we know that 95% of the data will fall within 2 standard deviations of the mean of our population, it means that in all likelihood that there's a 95% chance that the true mean will fall within 2 standard deviations of our sample mean. That's one of sort of the key points. So I want to pause there to make sure I have a graph for it. Right, but the important thing is we know, right? We know that the 95% of the data here for coin flips falls within 2 standard deviations above or below the mean. And if we take a single sample out of this data, there's a 95% chance that the true mean will fall within 2 standard deviations of that single sample. And so I draw that out here. So I'm drawing the same map of all of our coins. I'm taking 1 sample. So this is just 1 sample of my data coin. I'm taking 40 of them. I'm going to draw a line for where the mean is and 2 standard deviations around it. So this blue line is the mean of my sample. These dark blue lines are the 2 standard deviations plus or minus. And so we took one sample of the coin. We took one sample of the coin. It's a little bit above the mean. It's a little bit above the mean. But the population sample was within 2 standard deviations of that. And so this gives us, so when you hear a 95, the concept of a 95% confidence interval, you hear that phrase during elections a lot. This is the concept of a 95% confidence interval. So if we take this one sample of flipping a coin, it's 52. We're 95% confident that the true mean of this coin, of this population, is within 2 standard deviations of that sample. Are there any questions to this point? Okay. Okay, so that leads us back to the test scores. So we've got so we have this concept that we know the population mean falls within 2 standard deviations of our sample mean. And what that allows us to know is whether 2 separate samples are coming from the same population then. Because when they're coming from the same population, we say that they're the same. And when they're coming from different populations, like the idea of a population of unfair coins and fair coins, that's how we can identify them as different. And so I've got my two classes next fall, I guess. And in one of them I sing, and one of them I don't sing. And so in the one that I sang to, they get a 79. And in the one they don't sing to, they get a 74. And both of those numbers are within the normal range of data for my classes in the past. Classes have gotten 79 and done even better. Classes have gotten 74 and even worse. Right? All of this is just normal data, normally within the range of this class. But what I want to know is whether these two samples, whether the difference in these two samples was just generated by random noise, like flipping the coin, or whether they were generated by something different that was done, specifically my singing. I'm going to skip over standard errors for now. We can circle back to it if we get this. All right. So here is the two of them plotted out. The singing was a 79. The no singing was a 74. And so with both of these, I know that sort of the true mean for my class is going to be within 2 standard deviations. That if my singing group is different, the true mean for them is within 2 standard deviations of the sample mean. That the population mean for them is within 2 standard deviations of the sample mean. And I know the same for the group that wasn't sung to. And so if I draw those bars around it, sorry, I'm going to redo this because it got too different. There we go. So this is 2 standard deviations around the no singing group. This is 1 standard deviation below on the no singing group. Um, sorry. This is the problem with randomly generating data. Oh, I already did that. I manually created that problem. Okay. So this is the 2 standard deviations around my singing group. This is 2 standard deviations around my no singing group. And the 2 don't overlap. And so I can be 95% confident that if I kept taking samples of classes that I sang to, that the true mean for that value would be somewhere between these 2 orange bars. And if I kept teaching the class without singing, that the true mean for the group that's not being sung to is somewhere between these 2 orange bars. And those 2 sets do not overlap. And so I can be 95% confident that the singing group is different, that it's coming from a different mean, that if we kept taking samples of these, the 2 distributions would not overlap.
And why 95% confident as opposed to 98% or 90%?
So the 95% confidence comes from the normal distribution, because we know that 2 standard deviations contains 95% of the data. Or are you asking why do we care about 95% confidence?
No, that was it. I just wasn't
Okay.
sure where the 95 had come from. Okay.
Yeah, so the 95 is generated because we know that's what 2 standard deviations above and below gives you. Right, so I'm 95% confident here that the score for classes that I sing to is higher than for classes that I don't sing to. But I'm not 99% confident. Because if I added, so these orange bars are my 95% confidence interval. That the true mean, that this mean is generated, it's me acknowledging that this mean is generated somewhat by chance. That this isn't sort of the true mean for my class. But I'm 95% confident that if I kept sort of redoing this, that the test scores would fall within this range. That most of the test scores would fall within this range. The sort of equivalent is during an election. So you'll hear that Biden, going back a few months, right? Biden is polling at 20% nationally with plus or minus 3 points. Sanders is polling at 15% nationally, plus or minus 2 points. And it's because we're taking a sample. We're only calling 3,000 Americans to find out. And so we know that those 3,000 Americans aren't perfectly predictive of the country. But we're confident, we're 95% confident that within that range, 20 plus or minus 3, is the actual percentage that would vote for him if we kept pulling samples. If we called another 3,000 people and called another 3,000 people, if we kept collecting those samples, that they would cluster around 20 plus or minus 3. And that somewhere in there is the true percentage of support. In the same way that if I kept doing this for my class and kept singing to one group and not singing to the other, right? Other things will affect the test too, but over time, the sort of the mean will be somewhere between the 2 standard deviations above and below 79.
Can you go back to that
something that showed like, right, within, if you only take 50 samples or 100 or
Mhm.
200, they're all over the place, but at some point they become a bell curve. Yeah. That's what I still don't understand. I'm kind of in a place of like the mythology of the bell curve. Like it sounds like witchcraft to me right now, like kind of statistical witchcraft of like, I'm willing to just like suspend my disbelief and go there. And I feel like assuming that's kind of part of this is like, this is just stats theory, right? This is like, people have proven this mathematically over a long time. And at
Yeah.
this point we can just swallow it. But like, how do we, I was thinking back to this question I asked like weeks and weeks and weeks ago in class, when we were in person, of how do you know enough that you have a big enough sample, basically? So like, what is that tipping point, and how do we
Yeah.
manage?
So so the last question is sort of, we are closer and closer to being able to answer it. So to some degree, this is witchcraft. And I will sort of fully acknowledge that. So to some degree, when we get to the end of all of this and I'm able to give you a test that you can do to see whether waking up early makes you lose weight. And there is a test that will give you an answer, and it is either thumbs up or thumbs down.
Okay.
And that test is entirely reliant on sort of probabilities. So the thumbs up and thumbs down is just based on, it can never tell you, this is going too far on a tangent. It can never tell you yes or no. It can only give you the chances, the probability of a yes versus a no.
Mm-hmm, mm-hmm.
And just understanding that is completely okay. You don't have to understand all of this to understand that test as its sort of output. But then you're taking that test at sort of its word. And so to some degree, you have to take this at its word too. Right. So the reason, so so I'm sure it's proven mathematically somewhere. But we can see the central limit theorem work right in front of us. Right. As we take more and more samples, all of these individual samples of coin flips, we can see them form the bell curve. And we can do this with even more and more samples. And so that's what we do down wherever I just was, right? No matter what the data looks like, as we take more samples, it gets closer and closer to a bell curve. And so when we just get one sample, right, you can think about all of these as individual samples. The fact that if we took one sample from this messy distribution and we got this value, which looks like it was 68 or 68 and a half, right? That's not that close to the actual mean of this distribution. But it's within sort of a reasonable range. And we can see all of these form into a reasonable range as we take more and more of them. And it just,
So basically, if it doesn't form a bell curve, you haven't reached enough of a sample size yet.
yeah. And so you can see that here with the 100 samples. And so this is just using samples of 40, right? So that's not a large sample. If we took larger samples, it would probably be faster. Let's see what happens if we bump the sample size up to 400. Right, a little bit quicker. It looks a little more bell curvy on the 1,000. Right, and so, I mean, I think that the bigger, yeah, I don't know. I don't know. What, I don't know. I need your help. I need your help. Is any of this making any sense?
I mean, like from my perspective, I generally know what you're talking about. I know what you're trying to impart. I think it's interesting in a very theoretical sense. I could never do it, and I'm just like I still don't. I was just so proud of myself that I could finally run a bar graph in R Markdown. So I don't understand how you knew what numbers to plug in to come up with all of these graphs. And I mean, my only concern is not like I'm just trying to learn for the test, but I'm just trying to understand if there's a place where we can, like, do we need to know how to make all this fancy stuff, or is this again just theoretical?
Yeah, you don't have to understand how to make any of these graphs. So so the lab this week, okay, the lab this week asked for no coding. All I want this week is for you to understand what the central limit theorem is, which might be asking too much, because there are times when I'm not clear if I understand it. But sort of this idea. So next week, what we're going to do is hypothesis testing. So what we'll lay out is, so the idea is if I have a hypothesis that singing to my class will improve test scores, how would I go about actually testing that? Knowing that there will always be some randomness in my data. That my data is always capable of jiggering above and below the mean, right? I could have a hypothesis that blowing on a coin will increase the number of heads, right? It's the old idea of blowing on the dice before you roll them in craps. I don't actually know if that's why people do it. Anyways, let's say I have a hypothesis that blowing on a coin will increase the number of heads. And I test that by flipping it 100 times twice. And when I blow on it, I get 60 heads. And when I don't blow on it, I only get 45 heads. And so I conclude, right, that blowing on the coin has made this difference, right, because there's this big gap. But what the central limit theorem tells us is that we should expect the number of heads to vary from each sample. Each time we flip it 100 times, we'll get a different number. And that both of those numbers are well within the range of any coin we could flip. And so what the central limit theorem gives us is this sort of structure and language of understanding how far apart do two observations have to be in order to know that they are actually different.
Cool. I feel like I know enough to sit with this and go read the textbook and maybe listen to this again, but like, yeah. Okay. That's where I'm at with it. I don't know where others are. Yeah.
Yeah, I don't know. I think I'm towards the end. I don't know, what else did I do here? No, that's the thing I already did. So I have other examples I could pull out if people want to keep hearing me try. I would probably say, I think Liz is on the right track, that having all of this in the back of your head and then reading the textbook will probably do more than continuing to listen to me try and explain this. I do have an example of being at an event and trying to tell the difference between NBA basketball players and normal people, if anyone thinks that would help. Um,
I have a question about the singing graph.
yeah.
And I'm never really hungry for the sports examples, but that's just me. Thank you. Just going back to like, I hear you that they can't overlap. That's the like point of distinction you're looking for. But
Yeah.
they look pretty close on that singing one, singing versus non-singing. And
Let's see.
so, Mark?
Did I just read? Yeah. So okay. That was the wrong one. Is this the one? Go back. So yeah,
So that's just sort of my question is like, yeah, is
Yeah.
that what if they overlap a little, or is it just like a yes or no answer that you get? Like, what's the kind of, and how do you tell?
So I mean, so because this is all randomly generated, so let's take this example.
Mm-hmm.
Here we can't be, so it's possible that this mean for the singing group is actually down here, and that the mean for the no singing group is actually up here, and that I have pulled a random sample where it looks like the students that were sung to did better than the students that didn't sing to.
Mm-hmm.
But if I kept doing this, I would realize that my singing is actually hurting my students' performance.
Mm-hmm.
And so what we would conclude here is that we're not 95% confident that the singing group is higher. What these sort of bars, and these bars are somewhat arbitrary, and we'll talk about sort of how to use them as a test. This is just sort of a way to visualize the two standard deviations. But it's the idea that we can't, if the two cross, we can't be confident which is higher and which is lower, which of the two means is higher. If they don't cross with those two standard deviations, even if we pulled sort of an extreme sample from both, we would know that one is higher than the other. And so
Okay.
with this example, we would conclude that they aren't different. Even though we know the two means that we calculated are different,
Mm-hmm.
our worry is that sort of in the population, if we kept doing this, would we continue to see different results?
Mm-hmm. And it's not like you get like a answer like there's a 30% confidence XYZ. It's like either 95% or we're just not really confident.
No, yeah. So next week we will get a precise answer of how confident we are that the two are different. So we can see that the 95% confidence interval crosses here, but it might be that at the 75% confidence interval, if we just move, actually we can, at like the 75% confidence interval, that's how far apart they are. And so we would be 75% confident that the singing group is higher than the no singing. But there's still a 25% chance then that we're wrong about that difference.
Mm-hmm. Mm-hmm. Okay, cool.
Good question. Are there any other questions? Okay. Well, if there aren't any other questions, I think that's all I have. That is more than I should have thrown at you. So what I would recommend doing is looking at the chapter, working through the lab, and it might just take looking at a few different things to figure it out. And what I can try and pirate the chapter from the book that made this all make sense to me, and I can try and put that online. But at the same time, and let me like walk back that if you don't understand any of this, you can still understand the test we will do later. So all of this is useful, maybe, but not necessary next week. It's like the prequel. So this is the prequel to the movie. And you can enjoy the movie just fine without having seen the prequel. But there's something about sort of understanding why the character's doing that maybe makes it more fun. I don't know. I don't know what we're doing here. So any other questions? Any other thoughts? Anything anyone wants to say before we sign off?
Aside from not all prequels are good, I just want to remind everybody that the Google Doc link has been put in the Moodle site. And whenever I get stumped on something on the homework, I'm adding to it. So like, please use it and add to it. And then also, I'm still going to host homework time on Sunday. I know that's Easter. It's also in the middle of Passover for me and maybe some of you, but I'll still be there. And so if you need help with homework or past labs, like I'll have my Zoom open and the link is in the Google Doc.
Very cool. Thank you, Heather. Anything anyone else wants to say? I do realize now that calling this the prequel was insulting to myself. So any other thoughts this week? Otherwise, so next week we're going to do a lot. Next week, I promise next week will be so much more fun. Because we'll be able, so next week is where we will be able to actually start to see whether stuff matters. Next week is going to be fun. Promise. So, all right. Well, see you all next week. Enjoy the week without being required to code in the lab. Stay safe out there.
Thank you.